Yo. What's up, Today we're working on my custom OS written in Rust. Right now, it's not much. It's boots in QEMU in an x86 emulator. I assume it boots on real hardware too, but that actually hasn't been double checked. I can load it through grub, through QEMU's kernel command line, whatever. All it does right now is it like sets up a memory allocator, a logger, does some like serial and VGA output setup. Then like just kind of like proves that it can allocate some maps, read the clock, and write the clock, sleep for a little bit, handle interrupts, etc. And then close. So it doesn't do much. And the goal here is to eventually maybe like write some sort of like web server that's driven from this OS or something to have some way to interact with it. And then moving forward, who knows, like maybe I'll get bored or maybe we'll have some other things that we want to look into. So today what I want to look into is support for async functions. So what a kernel is essentially just this like way to respond to events that happen either from the user or by system hardware, right? So like maybe he's just kind of sitting there doing nothing. He's just kind of sitting, and we'll call this kernel. And then maybe somebody presses a button in the serial port. User presses this, that wakes up the kernel, and then maybe the kernel wants to like do something in response, like log press or something, right? And then maybe that goes back out to here. But once that's done, he's kind of just sitting there doing nothing again. And so this kind of like follows like this like event loop model pretty well, where like let's throw another example up. One sec. So maybe you're like a web server and you have like Ethernet, and like somebody issues a request from the outside world. Maybe the kernel goes and like fetches some data from the hard disk, sends it back over Ethernet, back out to the world, does nothing again. And maybe your like internal software model has like many of these connections coming in, many. And this is like the same thing as what like you would do, how you would handle this with like epoll or something on Linux, where you're like, I have like a ton of sockets, like they're all over the place, so all these different people, and I have like state associated with each of them, and I need to like check when anything happens on all of them. So you like say to the kernel like, hey, wake me up when any of these things happens, or like when any of these guys get data, and then I'll service them. And I think that you can kind of like imagine the kernel in like the same way, where he's just kind of waiting for a bunch of stuff to happen, one of many things, and when they happen, then he should wake up and handle them. And maybe during that process, he might like try to write to the serial port, and maybe run to the serial port right now. If I go into my serial implementation, we have this like busy loop in here that says like, while you're not ready to transmit, like we'll just wait, hot loop on you, and then we'll write. And that kind of thing fits better into this model, where it's like, I wrote one thing to the serial. Now I'll wait, and when it's ready, wake me up and I'll go again, write the next thing. And Rust's async model kind of fits well into this, and so I think it would be kind of fun to experiment with like writing my drivers around the async model. It does kind of lock me in to being async, but I think maybe that's fine for now and kind of fun. And yeah, I think that's what I want to do. So Rust's async model, when I'm talking about that, what am I talking about? What can I draw here? So maybe it's better to pop open some Rust docs, or maybe I'll write it down here actually. So what I want to be able to do is in main, you can write this function like async function do something. And maybe in here you want to like do expensive action. And what you can do here is if this is an async function, you can type like await on the end of it. And what that'll do is let's say I have like a few of these. So I have expensive action 1, 2, and 3. What this actually turns into something that looks a lot like this, like a state. It turns into like a state machine. So you'd have like your state machine, and you'd have like your current state, and this state might be like an enum that has like, A has like A data, B has B data, C and C has C data, etc. And basically, like, depending on which state it's in, it will be like, this would map to state A, this would map to state B, this would map to state C. It'll basically like create this structure for each of these. And then what'll happen is he'll have like a function that's essentially poll, and this guy returns like ready or not, essentially. So if this thing is ready to continue, like say I'm writing to the serial port and I'm waiting for the serial port to become like, how do I say this? If the serial port has like ready to receive data, then this will return ready, and then we'll move on to state B. Otherwise, we just like return and we come back and check again later. And so what you can do is you kind of like auto-generate these like maybe more complex state machines than you write by hand, but they become like very simple when all you have to do is do a sequence of actions. And you can even do like for I in 0 to 100, right? Like do expensive action, wait. Like you get these like what look like imperative programming, like just normal functions that go end to end, and instead you're actually getting the benefits of these like complex state machines. So that's what I want to look at. Most of this is already baked into the language, right? Like that async await stuff is already baked in, and all you really need to write is a way to run these things. So when I call like async function test, if I call this function, Rust will get mad at me and say like unused implementer of core feature that must be used. So what this guy essentially does is he generates a struct with the future trait in it. Sorry, wrong document I'm looking up. That basically has this like poll thing that just says like, tell me, I'll tell you when I'm ready. And what gets passed into here is the state machine itself, or the future, and this like context. And so this context is like the thing that we have to create from scratch ourselves. And really all the context is a way to access a waker, and a waker is a way for a future to flag to the system that it's time to wake up. So what'll happen is if I call, how do I say this? When I execute this, if it's like time to do nothing, like if all the futures I'm looking at right now have nothing to do, I'll basically just like sleep my CPU and I won't poll again until somebody says like, hey, come poll me. Otherwise I would just be like hot looping over all the like things that are ready to like that I think might be ready to be done, and then I'm back into the polling state. I don't want to be there. I want to be in like an interrupt driven state, an events driven state. So what happens is I look at my futures and I go like, oh, none of them are ready. Time to go to sleep, take a little nap. And then when an external event happens, like an interrupt, or maybe like in normal programming, like a thread finds something or epoll says something, you can then say, okay, wake up my event loop and like try to make progress again. And so all this guy is how do I create this guy again? This handle encapsulates a raw waker instance, which defines the executor specific wake up behavior. Right. So all I have to do is define these functions. So how do I clone my waker? How do I wake it? How do I wake it by reference? And how do I, like, what do I do when I drop it? And that's what we want to implement here. So I think what should be very straightforward here is that we can wake ourselves up by just executing an interrupt. Because I think what happens is my sleep mechanism is essentially going to be running core arch asm halt, which essentially says like, hey, stop doing shit, I think. Let's just double check what this halt instruction does. An x86. Oh, Wikipedia is not for sale. Yeah, okay, we get it. Close. In the x86 architecture, halt an assembly language instruction which halts the CPU until the next external interrupt is fired. Interrupts are signals sent by hardware devices to the CPU, blah, blah, blah. So we can kind of assume, maybe for now, maybe this will have to change in the future. But I think we can assume that if no external interrupts are fired, we have nothing to do. Because all ways that a user can input with the, like, interact with the system, like wiggling their mouse, typing on the keyboard, hopefully we can tie all of those to interrupts and say like, oh, something happened on USB, time to like check what's going on. Or something happened on the keyboard and they typed into the PS2 port. Or something happened on the Ethernet and we got like a frame in that you have to service. All of those should wake up the CPU. So I think that our core loop can basically say, we can say here we take in our future. So we'll say is a future. F is a future. And this is an F. And we can basically say while I think it's ready. Sorry, I should have remembered these words. Poll. Future poll. This returns a poll. So this is core from core task. Use core task poll. Poll pend while the future is pending. Sorry, one sec. Fut.pin box. Just like this. So this needs to be core future. Sorry, just trying to get the syntax like approximately right. What is this pin box? Why is this? Oh, this is a snippet? Oh, I see. Oh, I crashed my language server. Classic. Okay, so let's go back here. I think that I need to convert this into like a box? No. Pin, new. How do I make these like pins again? Okay, we're gonna do pseudocode for now. Our loop will look essentially something like, while we're pending, halt. Right? That's essentially it. And then when any external interrupt fires, we will just pull again. And maybe we should maybe try to like handle these like interrupts that aren't saying that we should repull, because probably polling might be like cheap but not trivially cheap. So maybe we'll say if some bool that's like flagged from the atomic, so if should poll, which will probably be in static space, right? We'll say like load this atomic. If we shouldn't poll, we halt. Otherwise we set like should poll false and restart, right? Essentially being like, when an interrupt happens, wake me up. I'll check if you said that I should be doing something right now. And if I should, then I'll do it again and we'll go back. So this is probably like this. There we go. So that's what my core loop will look like. And so now, what do these what does this raw Waker table thing look like? If this is my model, so I guess maybe should poll is not a static. It's something that we've like passed around the waker, thinking. Nope, this is just a static variable. So clone, I think our raw waker should have no data associated with it. So clone should be essentially free. Wake will be execute the interrupt that increments this, probably. Or maybe we just set the atomic and assume that the interrupt, like since we were woken up by an interrupt anyways, all we have to do is set the Boolean. Wake by reference, it's going to be the same. And drop, we have no data, so it should also be set fine. These functions must all be thread safe because waker is set in sync. Okay, clone, this function will call when it's supposed to get cloned. Implementation of the function must retain all resources that were required for this additional instance of a raw waker and associated task. Calling wake on resulting raw waker should result in a wake up of the same task that would have been awoken by the original. Okay, sure. This function will be called when wake is called on waker. It must wake up the associated task, blah, blah, blah. Wake. This function is called when wake by ref is called on waker. It must wake up the source. I don't understand how the... Oh, but must not consume the provided data pointer. So wake is allowed. Wake by ref is not allowed. Okay, sure. So I think this is pretty straightforward. So I think that this will look something like... Okay, so we'll make this atomic bool, which is static should poll is an atomic bool, and he's atomic bool new false. Nobody's woken us yet. What doesn't he like here? We know that this is invalid syntax, so let's comment that up for a second. Should poll is never used. Cool. So we undo this while loop. No method poll found for future f, right? Because this needs to be pin boxed or pinned. So I think it's like let pinned or let fut equals pin core pin new. Construct a new pin around a pointer of the same data type. So I think we just call this like this. So I've seen this trick before, where, okay, so what am I doing here? What is a pin? What am I trying to accomplish? So a pin is a way to say, hey, this value is stable in memory and will not move. And you have to use this like unsafe variant to create it in this context because it has no way to like guarantee this, that fut will not move. You're kind of like guaranteeing to it. And what we're doing here is we're wrapping this. We're saying like, since we're reusing the same name here, it's literally impossible for this thing to move for the rest of this function now because we have no way to like address it. And I think that if you look at the implementation of other places where they have like a pin macro, so I think like Tokyo pin macro, I'm pretty sure that this is what they do. Yeah, they just do pin new unchecked, take it by mutable reference. And yeah, shadow the original binding so it can't be directly accessed again. Easy. Okay, so we've taken this feature, and now we have this pinned feature, and there's no method poll because we put a semicolon here, and now we need to create our context. So our context is created from this raw waker, so let's set up our raw waker v table, which is what we were just going over. And this will have a clone function. Raw waker vtable. It's an unsafe function. So I guess here we'll start just like making functions here. So function raw, we'll call this waker clone. unsafe function, and he takes in a const this thing and returns a raw waker. Okay, and we'll just call this unimplemented for now. We have waker wake by ref. Both of these will be the same, so we'll just make that, we'll do one. And these will execute like some interrupt. Or maybe just set the bool. So these just say should poll store true and ordering. Oh no, I have to remember this again. So release, when coupled with the store, all previous operations come ordered before any load of this value with acquire or stronger ordering. In particular, all previous writes become visible to all threads that perform an acquire. Relax means no ordering requirements. Acrel has the effect of both for loads that use acquire. So I don't understand like the difference between Acrel and so the difference between Acrel and sexist is that there's the additional guarantee that all threads see sequentially consistent operations in the same order. How is that different here? Will all subsequent loads see data written before this? We'll see written before. So I guess it doesn't really matter, but that's odd. Odd. That's okay. So we'll just say this is release. My language server crashed again. Very cool. Okay, now we have a new function, which is drop. And this guy actually does nothing. We'll call this waker drop. Because we have no state, right? All of our state is external to the waker. And now we just have to figure out how to make a raw waker out of this. So we'll say raw waker has data, and we'll just say this is nothing. And raw v table is our create raw waker v table like this. Okay. Expected raw pointer const. So can we just say like std core pointer null, right? I don't actually care. This is nothing. And here we just need to make this function now, which is raw waker v table. He takes in nothing. He returns a raw waker v table. And all he does is create a raw waker v table with clone is waker clone. Wake is waker wake. Wake by ref is the same as wake because we don't consume the pointer there. And drop is waker drop, which is nothing. Okay. So we have a problem here where the raw waker wants to take in, a static. So we can actually make this a const function. And we'll say const waker v table is this. Bump, bump. Easy. I guess we have to set his type. And then here, instead of creating a new one, we'll just store the reference to waker vtable. And here we say waker clone with a null pointer. Because we know that that happens to not need to actually do anything. Make it unsafe. Which means that this guy has to be like this, and we say let vtable equals, or waker is this. And then we can make a context from waker. So let context equals core task context from waker. Doesn't like that? Why not? What doesn't he like? Oh, because this makes a raw waker. And then I need to make a waker from the raw waker, obviously. Obviously. How do I make one of these? From raw. This is so convoluted. I'm sure there's a reason why, though. So I'm not going to question it for now. He doesn't like this. Right, because this should be like this. Waker is this. From raw waker. What doesn't he like now? Cargo check. Expected raw waker found this because I semicoloned here. And this guy has to be like this. Because he's unsafe. Put the semicolon back, add the semicolon. And then here, now we can create a context. So this is core task context from waker. And I have to borrow it. And now here, I should be able to pass the context in like this. Consider reborrowing the pin instead of moving it, which does not implement the copy trick. Okay, let's see in more detail. Move occurs here because future has type pin and mute t, which does not implement copy. Okay, right, so here I just have to as mute here real quick. And here I have to declare this as mutable again. And here I can do is pending. Okay, so now we are now in a state where we are polling a future that's passed in. And we can just say, I guess for now, we can, yeah, we'll just say should poll store false, which is ordering acquire. And here we should load ordering acquire, and this should actually be release, my bad. And we call an unsafe block here. Okay, so I think actually, surprisingly, I think that we can run futures now. I think. And now we just need a way to test this. So let's construct a future that does not resolve until we'll basically like re-implement this sleep function, but as an async function. So he takes in the RTC and the time, he sets the end time, and then instead of being a function here, actually, he needs to be a future himself. So we'll say struct sleep future that takes in an end, or his like storing an end tick, which is a U size. And when we create a new one of him, which is a function new, which will take basically to be the same arguments as this. We will calculate the end here. And he also needs to store a reference to the RTC. So we'll say RTC equals and a RTC like this, and he has to be defined for some period of time. And here we need to tie the input RTC to that. Oh, I could probably just do this actually. I don't know, we'll see. We will see. So the RTC is tied to this lifetime, and we return a sleep future. Okay, like this. And now we just say sleep future end, tick is end, and RTC is RTC. And now we've like stored the stuff we need, and now we just have to implement the future. So we say impl core task future, or core future for sleep future, like this. And we implement the missing member. Output is nothing, right? We don't do anything. And then we just say on poll, we just say if RTC get tick is less than end tick, we return poll, what is it, pending? Yeah. Else we return poll ready. Like this. And I think now, if we replace this sleep here with a sleep future new, and we execute this feature now, which is fut. I think we should see the same behavior now, where we wait for 3 seconds before anything continues. We just have to fix this construction of this real quick. So this should be like this. And he also thinks that this should be like this. So I was constructing them with the internal fields, and really I should have been calling like new on them, which makes sense. And I think, let's see. Okay, we have to tell my environment where the compiler is. And now we're sleeping for 3 seconds. And nothing happened. Okay, so that's good. That would have been too easy. So let's see. So no one's ever calling wake. That's a bad sign. So let's think about this. Somebody has to, you see. So the reason that this is happening is because the interrupt's triggering in the RTC for, let's find it, updating the tick, and that's kicking us out of our like halt, but we would need in the interrupt, we would need to like trigger the new interrupt to wake. We haven't actually done that anywhere, right? Somewhere we have to set this bool to false. So let's for now do this. So we won't check the bool at all. And if I understand correctly, this should still work. And that does. So all we have to do now is set something up that tells when our sleep finishes, we need someone to let us know. And so unfortunately, I think that means that we need to like register our sleep time with someone. Probably the RTC driver. So we say, hey, RTC driver, in your interrupt, let me know when you are ready. Or like when I should be ready. Because like he's waking up every single tick. Boom, 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 boom. Okay. So let's think about that a little bit. Let me think. So probably here in RTC, I'll say like register wake up, right? And let's see. Wake up time, we'll say. And when he is finished, I'll just say end here, right? Then in the RTC, I'll like create this function and drop this in here. He takes in self and what would the other thing be? The time as a usize, wake up time as a usize. And presumably he would have some shared state with the interrupt. So we can say wake ups is a arc interrupt guarded hash map of hash set, I guess, of usize, which is from hash brown hash set. So we have like a list of times that we want to wake up at. And so here we say in our wake ups, we insert wake up time. Right? Now in the interrupt, what do we call this? Wake ups? So this is a arc new interrupt guarded new hash map hash set new. There we go. And now in the interrupt, we say what? If tick, so let updated, if up, or we'll say previous value, I think is the output of fetch and, if prev plus 1 is equal, or it will say if wake ups, we have to lock it, contains prev plus 1, we say create should poll is true, like this. So what doesn't it like here? Type must be known at this point, giving wake ups an explicit type. I spelled interrupt guarded wrong. And here I need to pass wake ups into here. And this is release, I think. One couple of the store. Yep, okay. So now, does this work? After 3 seconds, we exit halt. So that's good. So now we know that we can like, from our RTC interrupt, let's just double check that this is still using this. Yeah, so here, we can print line halting, just to double check. Right, so we're just getting rapid printing of halting. But if we polling, if we do this, or maybe we print how many times he's pulled this guy. He's only pulled him once now, and once at the end. So that's really good. That means that we have this thing. He knows that he's supposed to be sleeping for the vast majority of this. And then when he's ready, he wakes up. And let's kind of see now. Can I like see what the CPU usage of this is while we're sleeping? The poll time's too short. So let's change this from 3 seconds up to like 10, just so that we can see the effect on CPU. So like 15%, maybe that's fine to like handle all these interrupts. That does feel high, but maybe it's fine. I don't know. We'll see. Okay. Okay, so that's looking pretty good. We now have the mechanism to wake up. Now, a question that we should ask ourselves is if the RTC driver, like, does it make sense for him in his interrupt to hold this, like, should poll? Like, should he be accessing this directly? Where is this? Like, should he be doing this? And I think that's fine. I think maybe we'll hide this behind a like function in like a future module. But I think that is pretty reasonable, right? If we just called like wake up event loop here or something. And then the question becomes, is it reasonable for him to store the wake up times here? And I think it has to be, right? We could maybe abstract this away a little bit so that like the RTC driver itself isn't the one doing this. We could maybe like register like an on tick function that goes into the RTC driver, and then the wake up state is handled externally by some other class. Maybe that, I kind of like that, right? You would have like an on tick function that's passed in, and then you would just say on tick. And that actually lets us get like the state of system time out of here, which like also like our monotonic time, I should say. Like that also is kind of weird that it's like owned by the RTC. So let's kind of look down that road and kind of see how that looks. So first, let's just make sure that we like have saved ourselves in a good state. So say git checkout branch, a new branch that is related to async await. Oh, I'm just realizing I forgot to change the title of my Twitch stream. Oops, we'll call this implementing async await in my Rust kernel. Sorry about that. Okay. So now that we have, what was I doing? I was going to look into like pulling out this time tracking into its own module and pulling out like the future stuff into its own module. So let's do that first. We'll say source, and we'll just call this async rs for now. And we'll say mod async here. Escape async as an identifier. Okay, that's a bad module name. We'll call this async await, I guess. No, we'll call this, what's a good name for this? Async was perfect. Future, I guess we'll call it. That's fine. And we have to then move that file from async to future. So this is future rs like this. And in here, we need to copy paste a bunch of this stuff from main before. So here we had this sleep future and our executor stuff. All of this comes over here now. This is public now. This is public now. This is fine. We can actually use core future to clean this up a little bit and just remove core future here and here. And we should also use task. There's a lot of this stuff that we want to use here. So let's just get some of this stuff rearranged. Cool. And we use create RTC, or is it IO RTC? This. And now main is probably going to get mad because a bunch of the stuff is not used anymore. This has to be public. So here now we need this guy to be from future. So we say, I guess this ends up in here. Future, sleep future. And he also needs execute future. Okay, so we have this future, we execute it, and I think we compile now. Let's see. Okay, so now the only thing that isn't working is the RTC was directly accessing this atomic from the future area, and all we need to do now is just replace that with a pub function wake up executor, and this just says should poll store true is ordering release, I believe. And now in the RTC driver, I can just say wake up wake up executor, which requires me to use future wake up executor. Okay, cargo check. Let's take a quick peek. Cargo run. So we should still see ourselves sleep for 3 seconds. Now we're halting the CPU, waiting for an interrupt to wake up our event loop. That's not good. Did I increment the sleep to 10 seconds or is it? Oh, okay. I did just increment the sleep to 10 seconds and forgot. So let's put this back down to 3. It's just like a good amount of time to wait. And we're chilling. We are chilling. So we have now our future sleeps. He waits for the he uses the RTC driver as a source of time and tells him to wake up. And now what we want to do is we want to say, you know what? We don't like the idea that the RTC is like owning the like wake up of the event loop. That's like not really his responsibility. His responsibility is to read the RTC. And so what we want to do, first let's add a quick checkpoint. Checkpoint. And what we want to do is like the RTC driver should just have a thing that he does on each tick. So, or on interrupt, I should say. And the question is, what should that do? So we can have like a sleep management class, I guess. That seems kind of odd. Struct system time, maybe. And we have some sort of like function that's increment. Say calling him system time seems kind of wrong. We'll call him monotonic time. And he is just we want him to be able to live, be used by many people at once while still being updated. So we'll say that we have a tick in here who's an atomic usize, like we have in the RTC driver right now, which means that we need to import from somewhere atomic bool atomic usize like this. When we increment, we just take in a reference to ourselves, and we say self.tick store or fetch add, I think it's called. We fetch add 1 with ordering acrel seems fine. Okay. And what comes next here? So we have a way to increment, and we have a function to like get, I guess. And he returns the time as a usize, which is just a load from the atomic value in here. Ordering, I don't know, it doesn't really matter here. We could just be, maybe we do need to be a little bit intentional about the time here. I was gonna say relaxed, right? But if we're using this as a way to flag to the system that it's time to wake up our event loop, and then those like don't match up with each other, that would be a problem. So we'll say acquire here, which I think is when coupled with a load, if the loaded value is written by a store, blah, blah, all subsequent operations become ordered after that store. Perfect. What I was looking for. Okay, so now to get this out of the RTC driver, our RTC driver now will say, hey, I do something when the RTC increments. I get an interrupt and I like handle it. But one of the things that I'm going to do in there is I'm going to call this external function that you pass in. So we'll just call it like onTick, which is a function. And the function can be maybe just just like a function that doesn't have any inputs or outputs. That seems fine. And now to make sure everything compiles, we just pass in a onTick, which is this, I think. I think that'll work. So we pass in onTick. And I think everyone still compiles now. Nice. And so now onTick, what do we actually want to do? We actually want to increment the system time. So we'll say let system time, or monotonic time, sorry, is a monotonic time, new, and I just have to implement that new function. So function new, he returns a monotonic time, and he initializes himself with an initial tick of 0. So this is tick atomic usize. Do I have to type new here? Yeah, like this. Okay. So yeah, we pass in a monotonic time new. And on tick, we say monotonic time increment. And that's it. And now we'll do the same. Now we need to, how long have you been working on this? Like a couple weeks. It doesn't do much right now, but we're having fun. How long have I been working on this being the OS? A couple weeks. How long have I been working on today's goal of async await in the kernel? Like an hour. Yeah. Pretty fun stuff. Okay, so we have our monotonic time, and now we also need like some sort of like sleep management system. That's where we want to say, when I create a new sleep, I register with the sleep guy, and the sleep guy will then on tick say like sleep manager, we'll call it. I hate having manager names, but he does seem like a, or wake up storage, wake up list. Yeah, sure. And he is going to wake up if necessary. So when my sleep future starts, he'll like register with the wake up list, and if the wake up list sees that the time has incremented to the point where we need to wake up, he'll kick the executor into the right state. So let's just kind of like start stubbing that out and seeing what it looks like. And he needs a reference to the monotonic time, because the monotonic time is who he's going to use to get the info. So now we have a wake up list here. Monotonic time is a monotonic time reference. Monotonic time like this. And so now this guy has to have a lifetime associated with him. And now we need to implement wake up list. And I don't know if you can just like not specify lifetimes here. Let's try that. We'll create a new function, and he takes in the monotonic time. So monotonic time. Monotonic time. And he returns a wake up list with an anonymous lifetime that hopefully the compiler will figure out. And here we just say monotonic time. And now we need to create that like wake up if necessary function. So wake up if necessary takes in self. And he says in here we'll have like a list, or like we'll have a dictionary of all possible wake ups. This also has to be something that's like shareable. Otherwise, I won't be able to register new wake ups. So we'll say wake up times, and we'll just mutex guard it with an interrupt guarded. So we'll say, since we only have one thread, we don't have to worry about like actual locking. An interrupt is the only thing that can preempt us. So we'll just say we'll disable interrupts while we're using this thing. And in here, this is just going to be a hash map, hash set. Sorry, just like we had in the RTC. So then when we wake up, we say if monotonic time get is equal to, we'll say if we contain that. So if wake up times, let wake up times is the locked version of this. So self.wakeupTimes lock. If wake up times contains, or wake up times contains self.monotonictime.get, then we wake up executor. Oops, I broke my language server again. Classic. I don't know what triggers that, but it's fucking annoying. Okay. Wake up executor. So he doesn't like something. This return type is wrong. And here we need to insert wake up times, which is an interrupt guarded hash set. And now it's mad that I haven't used hash set, so we can just say use hash brown hash set. And are we chilling now? Missing a generic argument of usize, makes sense. And now we just have to say register. Register wake up time. And this will just be a tick here, and instead of contains, we'll say insert tick. And we don't need to if here. There we go. This needs to be borrowed as mutable. All right. All right. So now instead of taking in the sleep here, the RTC in our sleep future, we should take in the, like, what is this thing called? Wake up list. And I guess we also need the monotonic time, actually. We need both, which is annoying, but you know, it's the way it goes. And here we'll say wake up list is wake up list. Wake up. Okay. So start is monotonic time get. End is now so monotonic time actually needs to know his like desired tick rate. He needs to know what he's like, how often this is happening when the RTC passes it. So I guess for now we'll just say tick frequency is passed in as an F32. That's kind of annoying. I guess the monotonic time should own his tick frequency. So this gets a little tricky because I don't construct the RTC until I've constructed the monotonic time, but I also need to, the monotonic time needs to know the tick frequency that the RTC generates. Lucky for us though, this is just static, so we'll just womp. And the monotonic time just writes down RTC tick freak inside. Probably we don't even need to make this like a member variable. We can just say function tick freak. Well, okay, the way I've like trying to abstract this is I'm trying to keep these guys like separated from each other. I want the I don't want the monotonic time to know that he's associated with the RTC. So maybe we'll say we will just pass in tick freak for now. For now. And then it's up to the caller to handle making sure that they're registering the right frequency here. But that's okay, that's fine. It's not the end of the world. The caller is me, and I know. So here we take in self, and we turn an F32, and we just return self.tick_freak like this. Like this, tick freak needs to be passed in. And then here we can use monotonic time.tick freak. Here, monotonic time, montonic. This should be monotonic, not montonic. Monotonic time. Cool. So now instead of RTC registering wake up time, we say wake up list register wake up time. And here we don't pass in, we don't hold the RTC, we hold the monotonic time, which is a monotonic time. Like this. And then here, instead of saying RTC get tick, we say monotonic time get. And I think everybody's happy there. So now we can just construct this with monotonic time. Monotonic time, thank you very much. And the wake up list. Here we need to tell him that we're constructing him for use with the RTC. And let's use anonymous lifetimes here. See if he'll figure it out. He won't, so we have to set one here. We say this is going to be like this. Cargo check, I think. We compile, that's very nice. And do we run and sleep correctly? 1 Mississippi, 2 Mississippi, 3 Mississippi? No. No, we do not. Why not? Probably because the RTC, I haven't implemented his insides yet. So these functions can now go away. And this guy can go away, and this guy can go away. All he needs now is to call on tick, which means a lot of these guys can go away. Tick and wake ups go away from here. They're not used here. They're not used here. And we'll say that this also has to be static, so that it can be used from the interrupt handler. And then here we need to put these guys behind arcs so that they will live for as long as they need to. When all of them destruct, then they will go away. But for the purposes of this, they will live in the interrupt handler until the end of the lifetime of the program. So here we say, here, instead of making new ones, we clone the existing ones. We just have to make new names for them so that they don't, when we move them out here, we can still use them in the future. Wake up list. And do we compile? We do not compile because we need to import the arc type here. So use alloc vec, or probably here it's sync arc, I think. Nice. Nice. Cargo check. He doesn't like this. Binding monotonic time declared here. Value does not live long enough. Okay, sure. So the wake up list can't be bound to the monotonic time now. It needs to use an arc to him, which is a little annoying, but it's fine. It's fine. Probably there are ways to do this that are a little less heavy, but I don't think that an atomic reference count is really going to be making or breaking me here in this shitty little project. So here I just need arc clone on this as well. Okay, cargo check. Do we compile? We do compile. Cargo run. Do we sleep for 3 seconds? Let's go! Okay, that's sick. So code's looking a lot like nicer now, in my opinion. So now the RTC just has like this responsibility of interacting with the RTC, and when he gets the interrupt from the RTC, all he does is he just calls this external function. That external function is set up to increment our like global concept of monotonic time, which might end up in a static variable later. I'll have to think about that. And then now that we have like the latest monotonic time, we can say, hey, are any of the sleeps in our event loop, are they ready to be serviced? And the answer goes yes. And so he wakes up the executor, and our executor then will check this boolean. The boolean goes like, oh yeah, I'm good to go. Like, wake me up and poll all of our futures. We are chilling. Okay, that's really sweet. So sleep is like a good kind of like first target. But what I think like kind of like proves that this is like a good idea is if I can hook this up to the serial console. So right now, when I'm looking at like these log messages, what these are QEMU is emulating a serial console, and when I write to that serial console, QEMU like passes that on to standard output. And right now we have this like kind of like nasty bit of code. Nasty is the wrong word, maybe. Maybe like suboptimal, we'll call it. A little more favorable way of saying it's shit. Where we just like hot loop on reading the like line status register from this guy and checking if he is like ready to receive more. And so what I want to do is I want to like futurize this, right? Where really what should happen is I write to the serial port. Then what should happen is the serial port should like run an interrupt when it's ready to receive more. That should wake up my event loop, and my event loop should then continue with the transmission, which means that this like I can have like a async function write string, and this will have to be some sort of like future type that I haven't really thought all the way through yet. But yeah, that's where we want to go next. So first, let's just do a little checkpoint. Let's do a little cleanup here. So we'll add -u for commit checkpoint. And then let's like clean up these linter messages. So we'll just cargo format and cargo clippy. And most of these are unused imports. They're all unused imports. So I'll just do cargo clippy fix and allow dirty. And just make sure that didn't do anything like fucking stupid. So we still run, we still sleep for 6 seconds, we still come back, and cargo test still has passing unit test. Okay. So we will checkpoint that as well. Linter and formatting. And we're chilling. Okay. So let's look at the serial driver docs. So I pre-opened this earlier, but what we're really looking at is this is I don't know if this is the exact chip that QEMU is emulating, but it's something along these lines. I think that I read here that most common implementation of the UART is the 6650 UART, developed in 1987, and I think I saw somewhere that this is like the common one to be emulated. Its support is nearly guaranteed in PC emulators. That's what I'm looking for. So on this guy, there is a register somewhere that tells me what interrupts I want to receive. So let's see if there's like a register list somewhere on here that's easy to read. Here we go. This is summary of registers. Register address. So one of these is interrupt enable register. So the interrupt enable register, I can set if I want modem status, line status, transmitter holding, and received data. And so what am I polling right now in my serial driver? I am polling line status when I want to know if it's ready. So presumably, I should... enable transmitter holding register empty interrupt. This sounds a lot like what I want. Like when I'm transmitting, I'm finished. It's empty. And I'm ready to take more. And so I wonder what the line status interrupt is like different for. Then there's interrupt identification. So interrupt ID, interrupt ID, interrupt ID. So this will tell me if which interrupt I received, presumably. Presumably somewhere there will be a mapping on this datasheet of interrupt IDs to what actually fucking happened. Interrupt ID. Interrupt identification register. This could be used in a prioritized environment to indicate whether or not interrupt is pending. When bit 0 is a logic 0, an interrupt is pending, and blah, blah, blah. These two bits are identified the highest priority interrupt. Blah, blah, blah. This is bit 0 in FIFO mode. Spit along. So none of these really tell me. I thought this would say, in order to provide minimum software overhead during data transfer, character transfers, the UART prioritizes interrupts into 4 levels and records these in the interrupt identification register. Yep. 4 levels of interrupt conditions in the order of priority are receiver line status, data, received data ready, transmitter holding empty, and modem status. So this is what I'm looking for. When the CPU accesses the IR, the UART freezes all interrupts and indicates the highest priority pending interrupt to the CPU. While this CPU access is occurring, the UART records new interrupts does not change its current blah, blah, blah. 1 and 2 as indicated in table 5. Aha! This is what I want. So I want 0, 0, 1, 0. Transmitting, holding empty. Okay, so first we probably need to enable interrupts for this guy. Register an interrupt handler. In the interrupt handler, check if we're ready. And if we are ready, then wake up whatever future we're holding to write the next byte to the output. So let's take a look at that. So we're going to have probably like some sort of future. So we'll say async function write stir. And really this should be an async function as well, this write byte, because we're doing this like hot loop, but we'll think about that later. This will take in a reference to self. Does he need to be a mutable reference? I think no. I think nothing actually needs to be a mutable reference right now. Let's see what this guy holds. Oh, he holds ports directly. Never mind, he does. But this is going to be a problem actually. Because if I'm now registering interrupt for these, all of these ports have like exclusive access assigned to them. And we actually want these to be accessible from the interrupt, which means that we're going to have to wrap all of these guys in a interrupt safe synchronization primitive, which is fine. That works for me. So let's continue working through here. So this is going to be like the string it takes in. It's going to be owned because we are going to like hold onto this. Or it could be a string and just for the lifetime of the future, the string needs to be available to it. And in here, we're going to set up our like future probably. I guess really the only thing that we need async for is transmit empty. Right? So this could actually look like async function check. How do I say this? We could make a new one of these that's async. And he returns a bool. And in here, we'll say these unimplemented. And then our write string function just says I guess we don't want is transmitted. We want wait transmit empty async. And in here, we're going to iterate over each character and write byte. So we'll say self write byte. For character, well, characters may be a strong byte in s.as bytes. We're going to wait for transmit empty. And then we are going to write the byte. And that's it. Now the question is what does wait transmit empty do? Presumably, he's going to thinking. So the interrupt, we're going to be like sitting here saying we're not ready. And then the interrupt's going to come up and he's going to be like, boom, you are ready. And so really this guy can just, we only need to like register, like set the waker up here. So here we're going to say struct transmit empty waiter. And he is going to maybe have no state associated with him for now. Haven't figured that out yet. We're going to implement core future for this guy. And the output is nothing. And then what we're going to do is we're going to say, hey, when you are ready, let's see. Sorry. This is hurting my head. So the line status register now needs to be shared because we're going to pass it into this guy to check. His ready is basically going to be this. So here, self line status, or line status is an arc, interrupt guarded, so that he's safe to access synchronized. Port. Cannot find interrupt guarded in this scope, so we'll just start using that where we have a util interrupt guarded like this. And we don't have arc, so we use alloc sync arc. If this is equal to 0, we return poll ready. Else we return poll pending. Here we need to lock this guy because he's a mutex resembling type now. This guy needs to be interrupt guarded as well. I guess like realistically, he doesn't need to be interrupt guarded. Really, like this guy's like his internals. Let's look him up. Port manager. So each of these guys is doing like one assembly instruction that is interacting with this thing. And we know that for this guy in particular, there's no like synchronization of state with other registers or anything. It's not like we're calling like 3 things back to back and we need to make sure there's like no interrupts occurring in between them. I think that it's safe to just like use this directly. And I think that there's a type unsafe cell for this that basically says like, fuck it, we ball. Just let me use the thing underneath. So let's try that. Now, if there was multi-threading here, would we still allow this? I think it would still be fine. Use core, I think it's cell, unsafe cell. And we just have to be very careful with that, but I think I'm almost certain that this is okay. So we'll then say this is unsafe cell. Yeah, that's right. Arc unsafe cell port. So now here we just have to say line status is arc new unsafe cell new line status. So now we need to say, we need to call get on this guy. I think that's, and then dereference him. So get dereference. This operation is unsafe. So we write unsafe here. And we do the same thing here. Let yeah, here we go. Like this. We put the equal 0 here and we say let ready equals this, and if ready, we return ready. All right. So that's really it. And then we just need to make sure that when our interrupt triggers, we also say that we're ready to check these again. And we are only going to do that if we have somebody currently waiting on that. But we can assume, maybe it's fine to assume for now, that if we get an interrupt that says that it's ready for more data, somebody had just written data and somebody's waiting for more. I'm okay with that for now. That's like maybe like a little bit of an oversimplification, and we might wake up a little bit too often for that. But I'm okay with it. Fuck it, you know? Performance is not... let's say it's a secondary concern for this. So let's just do that for now. So here, wait transmit empty is just going to construct one of these guys. So transmit empty waiter. And he's going to take in a line status is... Hold on. The line status is arc clone line status. And then we just say waiter.await. Right, is that crazy? And this doesn't have to return a bool, it just... And now that I'm actually looking at this, I think maybe that arc shit... Oh, I was going to say it wasn't necessary, but it will be necessary for the interrupt part. So now, this guy needs to take in an interrupt... what is it? Interrupt handler is of type interrupt handler data, which means that we have to use interrupt handler data. And what we're going to do here is we're going to, in our enable interrupt control section, we need to enable, this is 0, 1, 0, 0. So, which is 2. Yeah, we're going to set this to 2. So enable transmit empty. Now we just say interrupt handlers register. Maybe we do this down here. How do we want to... We'll put this guy here. We'll say, we'll rebind let line status here. And then here, we don't need to do the arc stuff anymore because it's already done. And here, we are registering a lambda that needs to take in line status by move. So we'll say let line status is equal to arc clone the other line status. We have to pass in the interrupt number. So this is IRQ ID, which we want to use. Where is this guy usually hooked up? Give it a sec. Loading. 0x3f8. Oh, that's the port. But what about like the interrupt number? What is it? IRQ. Here we go. 4. Pick one element 4. And I think this is right. Okay, cool. And now we'll just say hi. Cargo run. Yeah, I won't like that. I guess what in here we say, we do this like check again. And if ready, oh no, we'll just wake up the interrupt. Wake up executor. We'll just do something conditional here. Wake up executor. That's all we're gonna do for now. We're chilling. And now just when we construct the serial device, we need to pass in the interrupt handlers. Which means all of this IO stuff has to come down below the interrupts, unfortunately. Here we need to pass in the interrupt handler. Which means here we need to pass in interrupt handlers. Like this. He doesn't like that for some reason, because this needs to be a reference. Now I think we should compile cargo check. We do compile. Okay, so now what we want to do is let's go back to the serial thing. We'll log here. Oh, logging here gets tricky. We'll put an info log that says hold here. And the idea is that we want to say that we're polled like once per letter approximately, not like nonstop. So here, if we say future is equal to what is this? Create IO serial SCD syncs. Hold on, stdout syncs dot serial lock. What is this guy's type? He's std syncs. And for now, usually this guy is not directly accessible. But I'm just going to get access to him. Oh, he is serial. He's here. stdout serial expect failed stdout not initialized write stir hello world. Okay, so what doesn't he like here? No field serial found its type std syncs. Why? Why? Oh, because I need to go inner. Who I will just oh, I can just deref him. Okay. So dereference him to get access to serial. Cargo check. What the fuck is going on? Serial unknown field. Ref cell. Oh. Borrow mute. And now he's saying write string is private, so we can just pub that bitch. Check again, and now we've got a bunch of problems here. So let syncs is this. We need to extend the lifetime here. And then we say stood out is syncs dot as ref as mute probably expect stdout not initialized, just some like lifetime management shit. And then here we say stood out write string probably. He still doesn't like that. Why? Syncs. Oh, serial. There we go. Now this guy's immutable. And that's chilling. Cargo check. We compile. Cargo run. Do we see the string hello world? So first of all, nothing's fucking happening. Which is concerning. Because a few seconds ago, this was working fine. Interesting. Okay, let's go into serial and see if this is maybe going crazy. So print line, hi. Nothing there. Okay, let's try not registering this interrupt and see if that changed anything. No. So what the hell have I broken? What? Like everything, almost everything in here should be the same. Unless it's this like unsafe cell shit. We could try this. No, because everything else is still printing fine. So we know serial is still working approximately as intended. It's the sleep that's not working anymore. I thought. Let's do this. Oh, okay. Okay. We're chilling. So all of this is working as expected, and then this guy starts not working, and I bet it's because this borrow is like conflicting with something. Let's try this. 1, 2, 3. That's not it. Okay, so I guess how would we find this out? How print line hi. 2, 3, and now exit, and then oh my god, what do I do? Jesus Christ, something went wrong there. What the hell? Okay, so we need to do a quick little hackaroony here, where we don't actually want printline to print to the console anymore because we're working on that, and it's making things confusing. So here we have printline or print.rs. Here we can just say don't write to serial. Okay. So now we can start printing stuff. We can say writing stir s. Let's take out this 3-second sleep because it's confusing. And nothing's happening. Print line hi Mick. Let's just see if we're getting anything out. Yeah, okay, so that's printing. Is this printing? What the fuck? Okay, so something's getting a little corrupted in here, eh? Okay, okay. So it's this borrow is just like fucking shit up. I guess probably what's happening is it's already borrowed or something. Oh, yeah, of course. I can't print while this is borrowed. Obviously. Oh, I can now. No, I should be able to because this is safe. Let's do this. Can I just print 2 high mix in a row? Uh, let's put this sleep at the end now. Sorry, this is debugging world. Okay. And we actually do want to execute this sleep now. Okay, so we got both high mix printed to the screen. And now if we try to borrow this, then do this, then print high mix again, that still works as well. That worked as well. And so it's only when I execute this feature that this becomes a problem. The second high mix is not printed. And it's just because this is borrowed here. So I can't print line in here, which is fucking frustrating. So you know what we should do is we should oh no, wait, no, that should be saved. What am I talking about? Because I'm not, sorry, my brain's not on. I was gonna say that I can't use print line in here, but I can because I'm not writing to the serial output anymore. Oh, but I am using stdout syncs. Okay. So probably just anytime I try to print line now, it's fucking crashing, which makes sense. So for now, let's do the same thing here, where we put these stdout syncs in an unsafe cell instead of a ref cell with no borrow checking, and we just allow the undefined behavior for a bit, just to get a feel, you know. So we do this. We do this, I think. And this is now like this. Okay, we're close. Unsafe cell, new. And borrow mute is not allowed, so we say, I think like this. Yeah. Okay. So let's see all the places where that's getting mad at me. Almost certainly this is undefined behavior, by the way. Like, I'm almost certainly ending up in a spot where I shouldn't be, so. Borrow mute not found for this struct, so stdout syncs is used here, so this gets like this, I think. Cannot borrow dereference as mutable. As trait deref mute is not implemented. Ugh. Okay. IO mod RS, so this has to be deref mute as well as deref, which just means that I copy paste this, write mute at the end here, and make this mute and mute and mute. Fuck. Hold on. Hold on. This has to be unsafe cell directly, like this. Here I return this. And then down here I need to do like this, and put them in, wrap them in unsafe. Jeez, Brust, man, sometimes you're frustrating, sometimes I love you, but holy shit, this is so tiring sometimes, man. This is like this. Variable does not need to be mutable. And here, this is no longer borrow mute, this is get and mute. Like this. Cargo check. Do I compile? Wow, I do. That's surprising. Writing string, hello world. Okay, so we're past the crashing now. That did help us, but we never get past this wait transmit empty. And it's because we have to bail early here. So we say, fuck. We need to say, if this is 0, we're ready to move. No dice. So what doesn't he like? Okay. So it's gotta be this, right? Print line waiting. It's probably stuck in here. Yeah, so he starts waiting and he just never finishes. So here if we say finish waiting, he never finishes. So there's something wrong with this. And it's because all of my fucking checks are inverted. So this, oh no. Oh no. So this should be not equal 0. This should be not equal 0. And in reality, this should be a fucking free function. So we should say function is transmit ready, who takes in the line status arc unsafe cell port by reference, I guess. Maybe we just take in the unsafe cell port by reference. And we return this. So he should return bool. Here we say, then we also say that this is unsafe, but that's okay. We know it's fine. And self should go away, so we go like this. And then we replace this. So we say ready is if is transmit ready self line status. And we can actually do this a few times. So we can say if is transmit ready, return. And I think that this is in the interrupt as well. No, it's not. Okay. Cargo run. Cargo run. Finish what? Hey, I think we're here. Print line. So let's get rid of these prints. Cargo run. Look at that, baby. Look at that. Async function. Oh. Okay, now what we want to see is that this poll is only ever called however many bytes we're writing. So hold will write here. And so we should see, weird that that didn't get written at all, actually. Oh, probably because transmit's just always ready. Waiting. Yeah, that's funny. So in this whole world, we actually never got to the point where we couldn't transmit fast enough. So I wonder if we can slow down our, well, let's also see if we're getting, okay. So here we're getting at least 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 interrupts happening, which corresponds with HELLO space WORLD. That all lines up. That all lines up. So really, I think we are chilling. I guess this waking up every character now maybe doesn't make sense. Okay, let's check if the executor is ever halting the CPU. It probably isn't. Future. Oh, but it's also fucked because I'm printing in between, and that's like slowing us down. Am I? Hold on, let's think about this. Print line here. Print line here. Power run. Do I see waiting ever? No. What if I write like something really long? Hello. Well, that's pretty funny. So I just actually can't execute fast enough so that this check was ever required. Which means it's fucking hard to test. Can I, but if I reduce the baud rate by like a fuck ton, maybe I will start to get this. So set divisor to 3, low byte for 38400 baud. Is there a way for me to like get it higher than that? So I think here, which register this is? This is the D lab. So somewhere is like enable D lab. This is, oh, divisor. Here we go. Divisor. Table 4 provides decimal divisors with crystal frequencies. So baud rate, I've set it to 3, and let's just set it to like 48 or something. Wow, still nothing. What if I set it to like 768? I don't understand. Oh, because it's too high. So let's set it to like 192. Wow, it's crazy that I'm not. I wonder if it's because like what if I disable in the RTC? Maybe like the RTC is like breaking us a little bit. So here I can just not enable the interrupts on the RTC. Still nothing. I was really hoping that I would be able to like see myself get this. How do I know that this is working correctly? So baud rate. The UART contains a programmable baud generator that is capable of taking any clock input from DC to 24 megahertz and dividing it to any divisor from 2, blah, blah, blah. 2 8-bit latches store the divisor in 16-bit binary format. These divisor latches must be loaded during initialization. Okay. So am I just writing the wrong byte? Which of these like are DLL? Oh, so is it something like I enable DLab, then I disable DLab? DLab equals 1. So here I set DLab to 1, and then probably I disable DLab after. So here I need data to be 192, and maybe I need to set the high bit as well. So this is the transmitter holding register. AKA, what the hell is this? Write only, read only, write only? Oh, I see. So 0, 1 is now interrupt enable registers. So here, interrupt enable, like interrupt or enable interrupt. Oh, here we've already done this. Oops. Okay, so let's go back to table 4 and try to like do something crazy. Right? Like 1047. So I don't know, let's just like pick a big number. It's weird that maybe it's that I would think that increasing the baud rate would make it so that transmit's not ready more. But maybe QEMU is like not ever signaling to the line control that it's not ready. Maybe QEMU is just like, I can take as much as I want. Oh, that's annoying. I was really hoping that I could prove this. Oh well. I think I'll have to find another way. And I'll think about this more. Probably I could prove it with standard input or something. But either way, I think that we've proven that the executor is working with the clock setup, right? That sleep future is working well. I think I've proven to myself, at least through like the code here, whether or not we can like prove that this is working. This concept of like writing async functions with composable weights in them, that's working pretty well, right? Like this function is nice to write, and this future isn't like crazy difficult. And assuming, sorry, just let me fix this, is transmit ready, self.line status. This would be a bool. Well, not is transmit ready, self.line status. Let's just, here we go. Yeah, as long, this was like pleasant to write. And so I think we've kind of proven that this will be like a way to generate drivers. The only thing that we need to like really hammer out is it would be nice to be able to merge these like the sleep and the print together in some way and make sure that like both are getting serviced well. So we can say fut2 is this guy. Right? Like this. So we'll say let fut2, and we'll say futures. Oh, I need to use the futures script. Cargo add futures. And we'll say futures future join fut2. Cargo run. We need to disable the std feature. So, futures are rs no std. 1 second. We're cargo toml here. Not this guy. This guy. So features default is here. So I guess we say no std features, but we do allow alloc ones. So cargo toml, and I think it's futures. We say version is this, and no default features, I think, is a way to do this in cargo. Possible default features is false. And then we'll allow the alloc feature, and then we'll kind of see how far we get with this. Cargo check. Waiting. Okay, so it doesn't like, this function takes 2 arguments, but 1 was provided. So futures We'll look up the docs here. There's a way to like merge two futures together. So futures. Join is what I was looking for. Futures, future, join. And oh, this isn't a vector. This is not join all. This is just join. Of course, of course, of course, of course. So I pass in my two futures here. And I run it. And hopefully what we should see here is we should see we print, we still wait for 3 seconds, and then we quit. Okay, that's really sick. I'm pretty happy with that. So what we've just proven here is that we can have like 2 asynchronous things running at the same time. These are like running through the executor that we implemented today. And we get to the end as we expect. So I'm really, really stoked with that. And I think that I'll call it there for today. I thank anybody who tuned in and is still here. And if you want to catch me live, you can catch me on Twitch around 2 Pacific. And if you miss me on Twitch, you can catch me on YouTube and catch up there. So appreciate it. Catch you on the next one. Bye.